Okay, good morning, welcome back. Happy Friday. Today is our 38th class. We are covering something called the definite integral. You've got no projects you're working on right now, but next class I will hand you the final project for the semester. It will be due at the start of the final exam, and then then 2 classes from now I'll hand you the last take-home quiz. Any questions on the calendar? Okay, so at the top of page 58, we'll start with our summary. In this class, we introduced the definite integral as well as the integral symbol. We also discovered that when it comes to rectangles, more is better. So in the demo, we start by reviewing something that we talked about before. So take a look at this picture. We saw that if that curve is the velocity curve, then what does the area under that curve represent? Distance traveled. Area under the velocity curve is the distance traveled. And so finding the exact area under there is quite complicated. That is a very crazy shape to try to find the area of. And so we approximate that area by drawing some rectangles. In this case, are these rectangles determined by the height at the left endpoint or the height at the right endpoint? The right, yeah. And so at each of these points, each of these intervals, we pick the point on the right. And we go up to the curve and we say however high the rectangle is there, that's how high the rectangle is going to be everywhere. And so those are right rectangles, 4 of them in this case. We could just as well have let the left endpoint of each interval determine the height of the rectangle. Likewise, we could have used the midpoint of each interval, or in fact any point in each interval we could use. Typically we'll just use left and right. In the last class, we saw this messy formula that the distance traveled, which was the area under the curve, is approximately delta t times f of t1 plus delta t times f of t2. Do you guys remember this thing? So each of these terms just represents the area of one rectangle. So that guy right there is the area of that first rectangle. F of t1 is the height. Delta t was just our symbol for the width. And then we go all the way to the end. The sum, that whole thing is called a Riemann sum, named after George Bernard Riemann. In number 4, it says we can use sigma notation, just like we did in the regression project, to abbreviate that long formula up above. Let's give it a shot. Okay, I'm actually going to put it in here because I got more space. So sigma notation. So we start with a big old capital S in Greek, big sigma. We just have to capture the pattern. Every single one of these terms looks like delta t f of t sub something, right? And the something is the thing that changes. So we just copy all of that. Delta t, put a dot for multiplication, f of t sub something. And then we just need to put a letter down there to generalize that something. We're going to use the letter I. And then the only other thing we need to do is put the starting value of I and the ending value of I. In this particular sum, what's the starting I? It's 1. And what's the ending I? N. So we go I equals 1 to N. In your regression project, I think it was I equals 1 to 3. There were 3 data points that you were playing with. Okay, so that is a very compact way to talk about the sum of not just 4 rectangles, but a general N number of rectangles, okay? All right, number 5, what can we do to get better and better approximations for the exact area under the curve? So before we look at the sequence of pictures, just in the first one, are these left rectangles, right rectangles, or something else? Those are something else. What are they? Maybe midpoint rectangles, right? How do we, like if we look at this particular rectangle right here, how did we determine the height of that rectangle? Well, it looks like the curve goes right through the middle of that top line. So here it wasn't a left or right, it was just use the midpoint of each interval, and that dictates the height. Okay, so there's 5 rectangles, maybe that's about 10, maybe there's about 20 or 30, I can't tell. But what do we notice about the area under the curve, which is what we're after, compared to the area that is the sum of the rectangles? Yeah, it's getting more and more accurate as we go to the right, yeah? Okay, and so like we said up above, the more rectangles, the better. In this last picture, I can barely even tell that like I'm missing some area that I want, or I'm capturing area that I didn't want. Okay, so down here, as n increases, remember n is the number of rectangles, the area of the rectangles approaches the exact area under the curve. All right, number 6. Here's the full-fledged, hardcore, no messing around definition for the area under a curve. If the function f is continuous on the interval a, b, and if f of t is greater than or equal to 0 for all t in that interval a, b, then the area under the curve y equals f of t over the interval a, b is defined by, and now we're going to define the area. It's the limit as n goes to infinity, summation I equals 1 to n, delta t f t sub I. So this is a kind of formula that they show like in TV shows when they're like kind of like somebody's having a math nightmare, right? And there's like equations chasing after them. This is the kind of thing that they put. But I want you to understand all of the pieces in this. What does this represent in our scenario? Area of how many rectangles? That is the area of one single rectangle. It's a generic rectangle. It's the rectangle at I, wherever that is. And then what does this piece add? It's a sum of the areas of all the rectangles. And then finally, what is this piece over here? Yeah, so we're going to make these rectangles really thin. That's a consequence of what this says, which says what about the number of rectangles? It approaches infinity. So you want the actual area, you're going to be using infinitely many rectangles, okay? So all three of those pieces may be kind of taken individually, not so intimidating. All right, writing down, okay, so here, 7. This formula isn't something you need to memorize, but calculating area under a curve is something we'll do many times, a few times this semester, and many, many more times in Calc 2. So we'll use some new notation to avoid having to write the formula above. This new notation is super important in any future calculus classes you take. So instead of writing all of this, we're going to introduce more compact notation, just a shorter way to write all of that. So here it is. It says we got this crazy symbol here. Let that symbol denote the area under this curve over the interval AB. So that brand new symbol, which doesn't even have a name yet, just represents area under the curve F between A and B, okay? Let's talk about the symbol. So it says that this piece right here is called a definite integral. The numbers on the integral sign, well, there aren't any numbers here, but the A and the B are going to be numbers in your activity. Those numbers are called the limits of integration, not to be confused with all the limits we've been calculating this year. It's a bit unfortunate we're using the same word limit here. And then the function y equals f of t, that is the thing that's sitting in here, is called the integrand. So just one quick example. Suppose that I gave you 1 to 3 x squared, t squared dt. So that crazy symbol right there represents an area. Area under what curve? T squared. Okay, great. I know what t squared looks like. It's this. So the area under t squared, but then from 1 to 3, t equals 1 to t equals 3. So this space right in here. Whatever the area of that particular region is, that's what we're talking about with all of these symbols here, okay? Yeah, I think that's good. Good. Notice that the curve, the area we talk about always goes from the curve to the t-axis, to the x-axis. We stop there. We don't go down forever. All right, so you are going to work through this activity, but I'm going to tell you that this activity is short and next class is long, so I'm going to stop you at some point here, and we're just going to start the next class's material, okay? All right, so let's see how far we can get in here. Again, if you don't have a graphing calculator, come up and borrow one. Trade me for your phone.